All right. So previously, we've talked about the famous three-step machine learning process: predict, calculate the error, and learn. Now, the middle step is something that involved calculating an error. And I glossed over that part in the last lesson. So, what does that mean, and how do we calculate the error exactly? So, to provide a little bit of context, let's briefly revisit something that we talked about with linear regression, right? So, here we had some data points, and our goal was to figure out which line best fits the data. In other words, we had to learn which line was best, because you could draw so many different lines through this data. And each of these lines, right, had a different value for the theta 0 and theta 1 parameters that are associated with it. So our algorithm somehow had to rank what the best values were for theta 0 and theta 1. So that word best is pretty vague, right? We need a hard criteria. So by best, what we actually mean is the line that minimizes the distance between the data points and the line. For example, this dark green line here is clearly better than this light green line below. Why? Well, because it's got a shorter distance between the line and the data points. So that's pretty easy to see visually. Now all we have to do is construct some sort of metric from that. What we need is a single number. And in this case, the number is going to look like this. What we're going to do is we're going to add up all the differences between the line and the data points. So the first difference might be 10, the second difference might be -6, the third difference might be 4. But because a data point below the line will have a negative value, right? That -6, what we're going to have to do is square them. So we're going to square all these differences and then add them up. And now we've got a single number. And we've also got a goal, right? So we've got this single number that has a name. It's called the residual sum of squares. And this residual sum of squares gives us a single metric on how good our estimates for theta 1 and theta 0 are. So with this in mind, we know that we can find the best possible values for theta 0 and theta 1 by minimizing this residual sum of squares. So we've given our algorithm a goal. If the residual sum of squares for one particular line is equal to 100, then that's a better line than if the residual sum of squares for a line is equal to 500, right? The lower the number, the better our line and the better our estimates for these coefficients. So why am I talking about this? Why am I going on about something that we've already covered? Well, we can think about this number as measuring the size of our error and expressing how good or badly we did. And this brings me to this lesson's word of the day, namely cost functions. Our residual sum of squares, or how it's also called the sum of squared residuals, is, you guessed it, an example of a cost function. And a very big part of the machine learning process is optimizing for a solution that has the lowest cost. So finding the best solution falls under this broad topic of optimization. And optimization is actually a word that you'll come across in many fields, not just machine learning. So if this topic of optimization comes up across different fields, it shouldn't really be a surprise that this idea of cost functions is also something that you're going to see across different areas, right? So you'll find it in statistics, decision theory, computational neuroscience, operations research, engineering. So you see it in many, many places. And this brings us back to this topic of jargon and language, right? because you have many different fields using different words for things that actually express a very, very similar concept, it can actually be a little bit confusing reading things or learning about this topic. So in order to make it easier, I want to introduce you guys to a lot of the jargon and a lot of the words that come back to this idea of cost functions right off the bat. So depending on the field and depending on the context, people don't actually always use the word cost function, right? And this can make things a little bit confusing, especially if you're reading an article online or a textbook of some sort. Sometimes you'll see these kind of functions being referred to as loss functions. And I've even come across people calling them error functions, but I think this is a bit less common, especially for this sort of application. And finally, you might even come across the term objective function. So in the process of optimization and trying to find the best solution for something, you'll often find the words loss function and cost function used interchangeably in many, many cases. But the word objective function means something a little bit more general, right? I mean, if you think about it, the objective isn't always to minimize the cost or minimizing some bad thing. Sometimes the objective might be to maximize a good thing. The relationship between the words cost function and the word objective function is kind of like how, I guess, like salmon is a fish, but not all fish are salmon. And I think that about covers the jargon, right? In machine learning, you'll mostly see the words cost function or loss function being used. And this is what I'm going to try to stick to in this course. Now, I don't know about you, but personally, I can't wait to jump straight into Jupyter Notebook and write some Python code. So that's what we're going to do next. We're going to take a look at how we can go about minimizing a cost function in practice. Stay tuned.